Welcome back. I always like to see happy faces after lunch. So I hope we need to be more dynamic now in order to not to let you fall asleep. Our next speaker will talk about the potential of quantum computing in banking and how far Raiffeisen Bank International is with this deep tech. Vjekoslav Bonic was always at the cross-section of business, digital, and innovation. He is the Managing Director of Raiffeisen Bank International's group Artificial Intelligence Lab or AI Lab and Head of the Digital Channel Interaction and AI. Vjekoslav, please take the stage.
Thank you. Yeah, good afternoon also from my side. My name is Vjeko, flew in from Vienna. Having the pleasure to try to wake you up after lunch. It's quite a hard topic we have chosen to do so. And I'll hope you had enough coffee. Let me start off with a question to all of you. Who of you has heard about quantum computing already? Hands up, please. That's a bit more than half. Very good. And who of you believes that this is something that's going to be ready in 10 years? Who thinks it's going to be ready in 5 years? Quite few. And I have to admit also with this opening that the topic is still an R&D topic. It's not fully productionally ready yet. And the reason why we started very early with this topic, I would like to explain. And also how we managed to actually even make it productionally ready for certain purposes, and try to also interest you in this field. Specifically, if you're coming from a data science area, you might find it particularly interesting, especially from data science with math background or with physics background. The things are getting really interesting, and speaking of interesting, Raiffeisen. Raiffeisen Bank International, I'm not going to spend much time. We're focused on from Austria and Eastern Europe, Central and Eastern Europe. My team is based in Vienna and in Bratislava, plus a few colleagues from the Belgrade team here. Very glad to see you all here. And what we all do together, aside of advanced analytics, data science, big data, AI, in the field of AI, we got interested in quantum machine learning and quantum natural language processing specifically, because that topic from the emerging technologies or deep tech fits perfectly to AI. And we'll talk about this a bit later. Let me start off with this rare historical photo, which is approximately almost 100 years old. You might recognize a few faces there, especially the gentleman in the middle, in the front row. And maybe also the lady in the third, on the left side, in the front row, Marie Curie. But the rest of these names are particularly interesting in our topic today. Starting from the left, Max Planck and Ehrenfest. These two gentlemen have founded the quantum theory around 1900, more than 100 years ago. And the gentleman in the middle has founded the mechanism how we speak, how we formulate quantum theory, used even nowadays in quantum computing. And those gentlemen to the right side, Heisenberg is probably known, or Schrödinger, and a few more, Born and Bohr. These guys have actually made it happen around the 20s, 30s. So basically, what we're speaking about is something that has been thought about and formulated 100 years ago. And even to this day, it's super, super complex to understand. And I admit I don't understand it. Why I'm speaking to you is because we have seen it work. And how many of you understand how a CPU and GPU function in reality, in detail? I studied IT, but I don't do this anymore. I don't understand it anymore. It used to. Not these days. And if you see the quantum computer, if you say you don't understand in detail how it works, it doesn't matter, it works. And we're going to talk about this today. Speaking of I don't understand it, another rare historical photo from 1948, I think, is this famous guy also saying that he doesn't believe in it. He even said it's spooky. One particular topic about quantum entanglement, which is two subatomic particles working at a distance. If you change one, the other one is immediately changed. It's quantum entanglement. That is something where Albert Einstein even said spooky, and this will never going to work. So even the most intelligent minds of this world have said it's not going to work. And it took almost up to these years, in the last 20 years particularly, to prove it that it works. And now the industry, if we look at it, somebody of you who might be interested in this field have recently heard from IBM announcing the 127 qubit quantum computer, kind of enterprise ready already. You can actually buy it, and some of the countries are doing this already. So that field is growing rapidly from 2018 on. If you look at the patents and the money invested there, it's an explosion of investments and also patents and research. So we're going to see a very interesting time in this area in the next 2 to 3 years. Now, going forward, I would like to speak about Mr. Beam. Mr. Beam, why? Because I mentioned this entanglement before. The entanglement means that if you have these two particles, and Professor Zeilinger from Vienna or from Austria, he has demonstrated this in end of the 90s, beginning of 2000, that across two parts of Vienna, this entanglement, and the journalists call it beaming, is actually working. Now, why is this interesting? Because if you change one particle and the other one exactly reflects that, on whatever spooky level of this universe, this works. Again, Einstein didn't get it, so I'm still not getting it why, but it works. You can also say that this can be used for cryptography. Very, very important. And there's another feature of this subatomic level. If anybody else looks at this two particles connected, in the moment where somebody looks at it, listens to it, when we talk about cryptography, the system is gone, it's changed, it doesn't exist anymore. Which means if it's connected, it's secure. The moment somebody tries to hack it, it's not possible because it doesn't exist anymore. And that's a particularly interesting topic in cryptography. This is why the next gentleman, let's call him Mr. Pan, he is the Chinese father of quantum computing. He studied in Vienna with the same Mr. Beam. And these guys have made something very, very interesting possible with the use of this Mitzius satellite that the Chinese launched end of 2016. These two gentlemen in 2017 made it via, from Vienna to Beijing, a communication over satellite on this quantum encryption level, which means you can now imagine why the Chinese are interested in this technology specifically, because nobody can listen to what is being talked there, which is not just on a military level or defense level interesting for secure communication, but also for us in banking, because security is one of the core elements of banking, customer trust. So whatever you do with a bank, it can be entrusted, which means it's also one of the interesting fields why we are interested there, is quantum cryptography. And that's exactly what these gentlemen have shown. And that this is not just mumbo-jumbo or fantasy or some academics doing something, is the next statement of this other famous gentleman, a CEO of Google, stating that the cryptography or encryptions as we see it today is or will be able to be hacked in a matter of the next 5 to 10 years. And that statement is from 2020. And that it's actually true is also something we have proven in one of our hackathons, which I will come to afterwards. Before we get there, another proof that you can Google if you just get interested in this field is looking at what the Chinese are stating. They talk about quantum supremacy. And also the US administration is pouring in billions into this topic, privately funded or publicly funded, whereas China And the EU, by the way, is more on the public funding, and US, UK, Canada is more on the private funding. But there are billions being poured into this technology for multiple reasons, not just cryptography and defense and the quantum radars, which can detect stealth airplanes. It's more also into this direction why we need it in banking for the very complicated algorithms. You might have heard about Monte Carlo simulation, Markowitz simulations, multiple optimization algorithms. This is what the quantum computers are doing really good. And not to forget the EU, which is, as a US paper interestingly also noted, yes, Germany got a quantum computer, but it's a US, an IBM quantum computer. What we have seen here, or what you can observe here, is a tech race amongst states and amongst companies. And before, in a few slides before, you've seen the potential interest because of cryptography. It might be because of other reasons, business reasons as well, but the states, the international organizations are investing a lot of money there, and there's a reason behind. Going forward, not working. Can you push forward, please, or this doesn't work? I spoke about public funding. What you see from the private funding field is names like IBM, Google, Microsoft. It's also even Intel, Honeywell, but you also see D-Wave, a very interesting Canadian company. And lately, I think it's 2 months ago that Amazon announced also to invest in an own quantum computer. So ultimately, you see public funding and private funding investing in various kinds of technology. You can do a quantum computer based on light, ultimately, or in supraconducting, minus 20, 170 something degrees, kind of similar computers which work on a subatomic level. Subatomic means it's crazy, it's spooky, ultimately. If anybody got a recent iPad Pro with this A15 CPU, I think, that's based on a 5 nanometers level. 5 nanometers, that's super, super small. With 5 nanometers, you get into a subatomic level, which means the things, how they build this chip, is smaller than an atom. And an atom is pretty small, much smaller than the coronavirus. And that means if you're going to build factories which can produce such subatomic chips, you are getting into this quantum state, which means in the next years, if the industry is going forward, speaking of big data and speaking of masses of communication, there is no other way than going into this subatomic level. And this is where we'll see quantum computing raising a lot of attention, raising a lot of money, ultimately, and why these big companies are investing hugely in that area. Very quickly, what is it that we're talking about here? One of the famous ways of how to explain this way of working is that a classical computer works on zeros and ones. Everybody knows that, a bit. In quantum, we talk about qubits. It's like, imagine a coin that you spin on a table. You click on it and it spins and it spins and it spins. You can't see if it's head or tail. Only if you do that or throw it in the air and do that, you will look at it, it's head or tail, 0 or 1. The thing is, while it's spinning, you can look at it, and what is it? It's a head, tail, and the combinations of all of it at the same time, especially if it's spinning fast. Which actually means, in the quantum computing world, you can look at all these states at the same time, which is presenting a nice opportunity of imagine all your computers in the zeros and ones there, and you can have a calculation running all possible states at the same time when you push the execute button, which means it gives you all the possible results at the same time, at once. Crazy, isn't it? but it is, and it works. And why this is interesting is another slide on the topic of industries who will be potentially interested. One of them is definitely pharmaceuticals, development of medicine. The way how quantum, not quantum computing necessarily, but quantum works is a depiction of nature. It's not the zeros and ones. It's below this subatomic level how nature works. If we can simulate on this molecular subatomic level how nature functions, then we might be able to develop medicine much, much faster, or even personalized medicine based for each single one of you. So we're seeing at the depiction here is showing basically which kind of industries, this is like from McKinsey, which kind of industries are using what kind of algorithms typically. And certain algorithms are perfectly usable for quantum. So when you simulate the DNA or the simulating molecular levels of how the human body works, then you're working at this nature level. And simulating with zeros and ones or simulating in this nature way is definitely something that is proving to be an added value. So we could see faster medicine. Another topic is batteries. Quite recently, there was an announcement of a company working on the quantum batteries. The problem of today's electrical cars is, of course, the reach and the charging time. What if the energy levels are boosted to multiple factor, plus you can reload these batteries in a matter of seconds, not hours? And a researcher on batteries recently said, to this day, we don't even understand how a battery works on a subatomic level. So they're kind of working with it, but they're not fully understanding it, which means such kind of computers can work in a very, very interesting way and much faster way. And to explain this, maybe a simple example of, I think you've heard about the traveling salesman problem. Something quite classical for everybody who studied IT, definitely have heard it. And when we take around 15 chairs here, and if you would put them in different order in this room here, and you would ask, starting from that chair, how fast, how much time do you need to get from the first to the last chair across the room? What is the shortest route? And if you take 10 chairs, you would have around 300,000 combinations. Combinations, how you can get there. If you take 15 chairs, it would be close to 87 billion combinations. Imagine now 20, 50, or 100 chairs, how you get there. And this is a problem that logistics has. One of the reasons why Lufthansa or Volkswagen or BMW is investing there, because of their supply chain logistics. There are so many parts that have to be combined into a car, coming from different companies. All these things are variations of something coming in at a certain point in time at a certain cost from a certain partner. A lot of parameters, and such quantum computers are perfect for such algorithms, but not for all of them. Same reason like you would not use a GPU necessarily to run your Microsoft Excel. Doesn't make sense. A CPU does it perfectly. But if you want to do some Bitcoin mining, I think you would rather to use a GPU. Same logic works here. You will have your CPU and a GPU and a QPU, which you will probably not have on your mobile phone, but rather will take it from the cloud, which you can do already today. For example, quite easy from AWS, Bracket service. You can use 4 to 5 quantum computer types and start experimenting with that. And this is what we did. We said, we're not going to wait until somebody or some consultant tells us, now it's ready. We want to experiment ourselves. Doesn't matter if I believe it's in 2 years, 3 years, or in 20 years. I'm seeing it as a moment where we should start getting ready for this, especially if we talk about cryptography, but even for the, let's say, its disruption potential and potential of using it for the benefit of, ultimately, of our customer service. So the reason, again, this disruption potential that we have seen, and we want to try it out, but also see what doesn't work. Skills, people. Finding a data scientist these days that is working on the cloud, capable of working on modern technologies, and even deploying things on, let's say, Kubernetes, is not easy for us. I have to admit it. We're looking for social, cloud, DevOps, system engineers, machine learning engineers, capable of working in a team and everything on the cloud. And now add to this equation somebody who understands the quantum theory, because in order to program a quantum computer, you should understand the quantum theory to at least a good degree. And not easy to find, and we will have a lot of struggle, not just we as a bank, but all of us. Just imagine how many students or PhDs are finishing quantum physics every year. I don't know how many, but I think it's a very low number. And that's exactly the kind of people we will need. And we managed to identify 15, 16 across our group. Very great minds. And we got them to work together on multiple hackathons. So my goal is internally to choose these right people, find them, and also keep them, but also to reach out to the community and say, guys, yes, we're a bank, but we do also doing some super modern stuff, and also constantly looking for candidates, even if it's not now, then it's in 2 years or whenever, because it's quite interesting stuff that we're doing there. And the ability to experiment there, if you see the faces of the team who is working on that, when they achieve to manage something on the quantum computer, you see it's like this pioneering field. It's something mind-blowing and absolutely great to observe for everybody who's working on that side, or for me as a manager. It's just a fulfilling act. So how we did it and what we did. We started off with the IBM simulator. We looked into the area of cryptography specifically. I think the team has managed in less than 2 days, and first half of the day was IBM explaining us how to use the quantum computer. That team I mentioned managed to break a 3 or 4-bit RSA code in a matter of 1.5 days. And this includes, or 2, this includes learning how the system works. The so-called Shor algorithm is exactly functioning as a reverse encryption. Basically, with all these combinations, like we said, if we have it 15 shares, like 87 billion combinations, and you get the result at once, you can imagine the encryption, how this calculated, this encryption keys, and you can actually reverse calculate them with the Shor algorithm. Now, this is the reason why Mr. Google is saying in 5 to 10 years, this breaking of codes might work. It's also the same reason why the NSA is telling us, no, don't worry about it, it's not going to work. And it's also the same reasons why some companies are starting to think about how to introduce a modular cryptography, because if somebody using this Wi-Fi here would take your data today from this room, just record the full 2-3 day stream, they will not be able to hack it, or not that easily, just looking at the encryption. But if they save this data and they look at it in 5 years from now, if they manage to do it, and they break it with a quantum computer, have you changed all your passwords? All your addresses, all your contacts? Probably not. And this is also the reason why, being a bank, we have to start thinking about this in order to secure our data flows, also for the future. Because it might happen in 3 years, 5 or 10 or 50, but it will be happening because we have seen it already how it works. More power of quantum computers will make this happen. And it's not just about cryptography. We had our fun with machine learning, some of the classification methods, the algorithms we have used basically, and learning parity with noise. It's a specific cryptography algorithm that we have used, and seen especially how the fault tolerance works. because it's not like you program it and you get one perfect result. You actually run it, it's called shots. You run multiple shots, 5, 10, 100, in order to see the best result based on a kind of a fitness function. If anybody worked with genetic algorithms have a fitness function, like any hyper-optimization. You describe what kind of result you're expecting, and then you run so many generations of this code to get the result. And this is similar how this works, basically. I could compare it to IBM mainframe from the past, but the majority here is too young to get the comparison. Our next hackathon, we call it hackathons because we get this internal team together, then we work for a week on the topics, was, okay, we checked IBM now, we see what works and how it works. Let's try the other kinds of quantum computers, because as you remember, multiple tech companies are doing multiple approaches. So we tried lonQ, which is working on trapped ions, different technology. We tried deep wave, Rigetti, so just to see how the other types behave. And they do behave differently, because every technology is kind of manipulating these atoms or subatoms in a different way. And understanding that, we have also understood that certain types of quantum computers, or companies if you want to say so, are good for certain problems and for others not. Which means we're closely getting to the moment of, let's find an algorithm that is small enough where we believe that the current power of quantum computers, again, we're not there that your mobile phone code can be broken, but certain things can be done already. And this is what we did now in September, October. We chose the asset allocation. Private banking field where certain types of financial instruments are being taken, and we recommend a certain investment behavior to our premium clients, which is, assets, different kinds of, you could say currencies. You have multiple currencies, then you have certain financial types like from stock exchange, or bonds, other kinds of types. You combine them all together, you calculate an optimum. And this is an optimization algorithm. And we got there, basically. This is what you see on the left upper corner. This is what the clients and the guys who are recommending these things to the clients are seeing. Green means invest, red means de-invest, and so on. Quite a simple topic, actually. And the optimization algorithm behind is, we believed and proven it actually, can it already work on a current quantum computer? And we made it. It works. I'll come to this in a moment. But it's a simple Markowitz optimization with multiple parameters. What we want to see: return, volatility, Sharpe ratio, if anybody heard about that. And ultimately, let's not go into the formulas because I couldn't even explain, to be honest. But the result ultimately is this, you see these dots in red and blue. These are explaining the results which hit certain parameters or don't hit certain parameters. And it's all coming to an optimum, which you can't really see here because it's in a too light color. But somewhere in the middle of this crosses is the optimum of the Sharpe ratio. And you see here, it's not perfectly hitting the optimum because this is from an older version of the so-called solver, Qubit solver algorithm. And the new version is being calculated right now, because when we started this in September, it was on a 2000 qubits, which is a different calculation level because it's a quantum annealer, another type. And now we got a 2.5 times stronger version, plus new algorithms, which we're testing now. Which actually means, as we speak, I'm certain that there is somebody, most probably in the US, thinking about how to upgrade the next version of the quantum computer, which we'll potentially have in a month or two. It's that fast how the field is evolving. So we have made it to take this optimization algorithm, and we haven't put it live in production now because we said, okay, it's too much effort now to combine the data, send it to the AWS cloud, send the result back, because for this algorithm, it doesn't pay off. But we could. And we could say it's an already first production quantum computer. I could state this, but it doesn't make sense. But it will make sense if we take some other algorithms for encrypting the communication between the major hubs of our bank, core bank systems and certain systems. There's other aspects for ML. One of the teams that I'm working with is busy with natural language processing specifically, conversational AI as we call it. Now, if we talk about quantum NLP, then again, the way the nature works. So the simulation of quantum walk neural networks, QWNN, or certain algorithms of deep learning. Deep learning is simulating how the brain works, neural networks. Now again, quantum is how nature works. If we change the technology, not about zeros and ones, then we don't have to simulate how the brain works. We're getting to the moment how the brain is working, which means there's a whole new field of deep learning or quantum deep learning to be enabled. And for me particularly, the NLP part is interesting because for the chatbots, for the voice bots, for the contact centers, because people still keep calling the bank, and some of these things can be better serviced if we understand the clients better. The typical case of asset management and even trading, when you have one of the biggest investors in this technology is Goldman Sachs. And you might have heard it's a big financial institution running portfolios, assets, investment funds. And what you have, if you take the whole world as your playground, and all the stocks, and all the companies, then you start calculating these crazy financial instruments that we don't even understand. Then you're doing heavy math. And this heavy math of asset and portfolio optimization is again the home turf of quantum computers. And it's no surprise that Goldman Sachs is one of the biggest investors in this area. And ultimately, let's generalize the topic, it's simulations, all kinds of simulations, not all of them, but most simulations and optimization algorithms can be of a huge benefit if you run them on a quantum computer. Now, if some algorithm takes 1 hour and you do it in 30 minutes, you might say, I don't care. If you look at this algorithm in detail, this optimization algorithm, and you remember what we said, if we take the 10 to 15 shares, now, of course, I can make the algorithm happen for the 15 shares, 300,000 to 87 billion combinations, which is a huge impact. I can change the algorithm to not give me the mathematical optimum, but somewhere close there, which means my calculation is finished fast enough, but I don't really get the mathematical optimum. And the question is, do you need it? Because if you want to drive from here to I don't know, Berlin, your navigation system will give you the optimum route, right? If the optimum route would be based on so many other parameters, like even let's take into account the weather and the certain prices per country, per region, the exact behaviors, maybe it's not the optimum route, but it's one that your system can give you in 20 seconds, 5 seconds, 10 seconds. Would you let your car calculate for 1 hour or 10 hours to give you the really optimum route? Probably not. But if you're calculating the core capital of a bank, which is to be counted in billions of euros, and if a quantum-based calculation can prove that the mathematical optimum is lower than the current figure, and you save 100 million euro, or 5, or more, that begins to be of a value. So my point is quantum will not be used for everything. Imagine the CPU, GPU, QPU. So for Bitcoin mining, again, the GPU, this is the reason why NVIDIA, one of the reasons why, the stock exploded. For QPU, we will for very specific topics, and probably in our private life, we will not see it soon, but you never say never. And certain usage patterns for certain technologies. And it's important to understand it. So to come to an end, and also leave some time for discussion, for us in the financial industry, the industry is huge. If you talk about financial industry worldwide, from Goldman Sachs to RBI, there's a gap of a lot of banks in between. Looking at that, there is a lot of potential looking at the industry as a whole. In addition, if there is potential and if we see the technology coming up, then we decided for us it's time to start investing. And as I said, we found a little team, let's say a bit more than a dozen people, who are coming together regularly, working on this topic, advancing our knowledge and understanding step by step. So I can only recommend this to everyone. If you can't find those people, then there are first companies coming up on certain markets at least, so small consulting companies. One of them we worked with as well, that actually can help you with this, to experiment, and then just take some internal algorithms and start rewriting them in quantum language. There's a Python library called Qiskit, for example, which you can use already to start. So ultimately, we said if we would wait for McKinsey to come to us and tell us, hey guys, to our board, now it's ready for quantum computing, it will be too late already. It will take us time to understand, we will do some mistakes, and if we would want to hire these quantum physics PhDs, I'm going to be afraid of the price tag we will have to pay, and we will not be even able to keep these persons. One thing is getting them, the other one is keeping them. So again, my internal motivation is to understand it, identify the right people, and also to keep them. And I believe this is also going to be a competitive advantage for us as a financial industry. Last statement. I'm guessing that you're confused. I'm guessing that this has been a lot, but I hope you leave this presentation confused at a higher level. Thank you.
Let's see first if somebody wants to ask the question before I start asking. No, I mean, oh, yes, we have one there and then the other here. Can we get the microphone there at the very end? It's less than 87 million combinations.
Thanks. It was an interesting talk. I'd like to rewind just for a bit to the beginning of your talk when you mentioned the global race for this quantum supremacy, how different countries and regions are in a race. I'm wondering, what do you think, how much is research and knowledge being shared across the globe? Because everyone has their own interest in this, so obviously a lot of this is kept as a secret. So do you think this could change for the better, the knowledge sharing? And yeah, how do you comment on this?
That's a very good question. Let me turn to this appendix on the. There is a slide I've put here to some proof on the millions and billions that are flowing into this. Seeing this private spending on the left side and the public spending on the right side. I hope you can see that. Now, whenever we have the private spending, there's obviously no exchange. With the public spending, which means academia investing in this. I mentioned Professor Mr. Beam, like he's also called, so Anton Zeilinger, aka Mr. Beam. He's working with the Chinese out of academic reasoning. There is an exchange there on that field. And I think particularly there are some NGOs that are exchanging things, but this is like beginning to be a really sensitive topic, especially if you talk about cryptography. And now imagine how there is the United States and others who are banning trade on certain cryptography elements already these days. And for this, we will see the same thing for specifically cryptography. On other fields, like quantum NLP, for example, it starts, the exchange starts, and will be crucial for understanding it, because I don't believe that a single country has enough mind to really, advance the whole thing. So collaboration will be crucial, but I'll be seeing it rather in the academia and not so much in the private field.
Okay, we have one question here.
Thank you very much for this presentation. In one of the photos you show one picture. I think this is your demo equipment with 3 computers with the footage like this stage. Mm-hmm. I think problem is with cooling. Okay, this is not your problem. This is your problem of suppliers of your equipment. But in your opinion, what in the future will be, let's say, how far and how fast we will approach to the zeros, because now for cooling we need temperatures below 200 degrees of centigrade, if I understand correctly. What is your opinion? I know this is not your field of expertise, but just estimation.
I really can't say. Just stating that if you look at IBM, and let's go a few slides before this, IBM and Google view here, that's D-Wave. Let me compare this here on the slides from before. No, here. You see this? This could be hanging here on the ceiling. Actually, it's beautiful. It's pure gold, like super cooled, and it's kind of manipulated with microwaves. So it's super sensitive. Like everybody has heard about CERN, this, in Switzerland, this beautiful spinning thing that cost billions. Why is it underground? Because every single influence from outside is killing it. And these things are super sensitive, and even supracooling something is also complicated at the temperature. So, but the one on the bottom here, IonQ, they just went live on the stock exchange in September. They don't need, it works at room temperature. So different technologies are using different approaches to get there. So the answer could be already now, because not all of them are using the supercooling. And we don't have to talk about green and emissions and everything. Supercooling is energy intensive. On the other side, you don't need a full data center because you can get results faster in some future.
Thank you.
Okay, we have questions there. Two questions actually from two guys.
If it's not about the formulas, I'm fine.
Thank you on your presentation. It was great. Since I'm coming from the finance industry, I have questions regarding the usage in finance. Is there, to your knowledge, any big financial institution currently using quantum computing to do actually portfolio optimization or asset allocation and similar things?
Morgan Stanley, Goldman Sachs, I think BBVA, as the Spanish say, HSBC. There's a list. If you look on the, I think you will receive the slides afterwards, and you see I had some fun here with the slides. Here is a recommended reading if you receive the slides afterwards, and there is particularly, I like the BBVA box here on the first one, bbvaopenmind.com, and they explain quantum computing from their perspective. They give some further links for reading, and I particularly like the McKinsey monitor, which is kind of where is it being invested, explains a little bit of it, and for financial industry, the Boston Consulting from 1 year ago actually, presentation, and there's an overview of which banks are invested in this, but If you Google for long enough, you will find it as well.
Thank you. And one more short question. What's your opinion on quantum computing replacing actual portfolio managers? And how long would it take, if positive?
I'm not sure to what degree current algorithms and high-performance computing has replaced the old portfolio managers, because you still need business know-how combined with the quants, as we would say, and the quants hitting not the quantitative but real quants are getting into this interesting position now, and you still have the business knowledge plus the techie part that is necessary. So I don't see any replacement. Advancement, I would call it.
Okay, thank you.
It was a really inspiring start of presentation. Thank you for this. I have a really fetish for some of these scientists. And I have some more theoretical question about how safe to develop some practice that not fully supported by theory. And you say later, some scientists for today also mean that is this theory not fully developed, like for example, strong theory is not fully proven, and all this quantum space and fundamental things is based on this theoretical concept. For example, like distribution theory, on one of these slides you show us that quantum computing really represents some of VAR models that is fully supported by normal distribution, if I'm not mistaken. And this is not always true in real life, because there is no scientist who already proven this. And how is safe to develop this complex technology with no theoretical support?
I use a certain wording here. Whatever. We call it, here it is. For us, we started this journey around being interested in deep tech. Let's see how it works. Then we came to the conclusion what kind of knowledge is needed. Then we came to this valley of tears. Let's call it change management. Say, Jesus Christ, how are we going to do that? And then we started learning step by step. And the QBO, the quadratic unconstrained binary optimization algorithm, is something that actually can run on GPU as well, or on a CPU. So for us, it was unknown theory. That is my point. For us personally, nobody from the team knew this algorithm. You know, like with Stack Overflow, something you just take it, see how it works, and so on. And you start getting into the theory, not me personally, but somebody from the team, and they're looking into this and learning new theories. Do we trust it? Not everything immediately, but you try with the current eyes and current understanding to see how the quantum computer is working. I personally believe that some of these, let's say, advancements or algorithms we don't even understand today, because if you look at also the libraries, in C# you have a few things, or in Python, not everything is programmed. These days, if you do normal computing, you will... a colleague here told me yesterday about this Codec AI, or was it Codex? No. OpenAI Codex, where you can type the algorithm and it spits out the code that you need. Just take it. It's by far not there yet. We're working on a very basic level. If you have ever programmed in assembler, with these registers and the whole thing, it kind of gets there. So some theory still needs to be developed. And I still think, personally, we are looking at it from current constraints of today's understanding. And some of it works as is, and some of it still needs to be developed.
And for Anne, what is your opinion about safe of these things? Is it safe or not?
What do you mean by safe?
For example, there is some group of men who can hack because they understand more than you.
Well, if you believe the NSA, don't worry, it will not happen.
Okay.
If you believe me, or Google, I wouldn't be worried now, but I personally think, about the statement from Google, I think it's true. In 5 to 10 years, they will manage to break the code. And if anybody, whoever is the first person here, managed to break the blockchain by using a quantum computer, then the blockchain will be gone because it's based on trust. And if you don't trust the blockchain, then the whole blockchain is dead. So the technology is super powerful, but I would not be, trying to make any panic here. But in 5 to 10 years, certain things will be possible. And I'm not sure if we're going to be the first ones who find it out. Because who is interested in that? Certain agencies.
Okay, thank you.
Any more questions? So I can ask the final two. When you mentioned blockchain, would the quantum computing be useful to make more energy efficient blockchain, or would it completely replace that idea with something new? What is your take?
Well, I'm not familiar with the algorithms of blockchain and mining itself. It might be if it's certain optimization algorithms or hyper optimization. I don't know how the blockchain exactly is calculated. I couldn't answer this question. If it's so-called NP complete or NP hard algorithms, then yes, could be significantly more efficient. But I've heard from what I've read, it's rather the opposite kind of thing, that it could be used for breaking the blockchain
rather than
building it.
Yeah. And the other question is, you asked us all about what do we think about when is quantum computing going to happen in 5 to 10 years. What do you say?
We have proven it 2 months ago with this here, that it's ready for certain things. Ready for my taste, I believe in 2 to 3 years. Is anybody here from IBM?
There will be tomorrow.
Nobody. Good, because I'm not sure if this is public. I found it on Google, so it must be public, right? Last statement here before you leave for the break. We started in 2018. The first quantum computer, 27 qubits, we tested in 2019. The one in the middle from 2020 we left out. And now they announced it 2 weeks ago, the 127 one, the Eagle. And this roadmap I've seen in 2019 already, in the early 2019. So they managed actually to keep it up, which was a surprise to me, because you see the sales roadmaps, was like, okay, sounds nice. But they actually managed it, because this picture is really quite old for me already. Now looking for 25 and beyond, it says 1,000 to 1 million qubits. If they can make this happen, then I would answer to you, well, in 5 years.
In 5 years would be your final answer.
Yeah.
Okay.
For super enterprise use. For certain topics like algorithms we said today, already next year.
Okay. Thank you. Thank you a lot. May I provide you with...
Thank you.
That is Vjekoslav Bonic.